When it comes to interesting numbers from mathematics, most people know the classics like pi, the golden ratio, or the Fibonacci numbers. Such constants are especially interesting because they show that mathematics is not purely a human invention, but in a certain way a discovery. Humanity has agreed on a certain form of mathematics. A set of basic definitions has been established, such as the choice of the decimal system. All of that could have been done differently. Mathematical relationships, laws, and constants already exist and are simply discovered. Pi is the ratio of a circle's circumference to its diameter. Without pi, many calculations in science are unimaginable. Pi has infinitely many decimal places. The 100 trillionth digit is now known. The effort to calculate it highlights how remarkable this number is. Or the golden number. It appears everywhere in nature, from atoms to celestial bodies. The Feigenbaum constant, sometimes also called the Feigenbaum number, is unknown even to many mathematicians. It describes a very interesting phenomenon from chaos theory and also appears in many areas, such as in a person's heartbeat or in a liquid. For some, the Feigenbaum constant is as important to chaos theory as pi is to geometry. Why is the number important? To understand that, you need to know what happens in chaos theory. Chaotic states seem to have interested people from early on. Even Leonardo da Vinci knew about the chaotic behavior of turbulent flows. Experiments on turbulence origins have only existed for about a century. The study of such seemingly unpredictable dynamic events in nature was the beginning. But the trend really started with a simple idea. One of the pioneers of chaos research, mathematician and meteorologist Edward Lorenz, made the so-called butterfly effect known in the 1970s. It describes the possibility that small phenomena somewhere can cause major events elsewhere. The following metaphorical question is often used for this. If a butterfly flaps its wings in Brazil, could it trigger a tornado somewhere else in the world? This thesis's development also explains chaos theory's origins. At Harvard University, Edward Lorenz completed his master's degree in mathematics, worked on weather forecasting for the United States Army Air Forces during World War II, and later became a professor of meteorology. It was the year 1961. At the institute, he worked on a weather forecasting model with the three variables: temperature, air pressure, and wind direction. First, he performed his calculations using the number 0.56127 and got initial results. On another occasion, he accidentally left out the last three digits and ran the simulation using only 0.56. So he made only a tiny mistake, but the result was completely different. So he came to the conclusion that in such deterministic dynamic processes as a weather model, small changes can lead to significant differences. So there is a connection, so it's not chaos in the sense that we would understand it. The connections are highly complex, but they do exist. That's why the same result will never occur. This opens the doors to chaos theory. The paradox, as already mentioned, is that chaos theory never deals with pure chaos as we would understand it. Because as soon as you can describe it with a theory or perform calculations, it's no longer chaos. So chaos research is actually more concerned with order within a system that appears chaotic. The weather can't be predicted accurately for more than a few days because there are too many factors that influence it. Maybe humans will never be able to describe all the relevant variables of the weather. But in every region, there are typical stable weather patterns that keep appearing. These can be described mathematically, and look, order was found. Another example is the dripping faucet. In the simplest case, it's very orderly. The same amount of time always passes between two drops. The more we turn on the faucet, the more complex the whole thing becomes. At first, the interval between two drops gets shorter, and now the drops sometimes start to fall out of rhythm. Turning it on fully gives you a stream of water. This is completely chaotic at first. There's no periodicity anymore. You can still see a clear overall shape. Another example of a chaotic system is traffic. Today, you can't calculate when and where a traffic jam will occur. Even the orbits of planets or moons cannot be calculated endlessly in advance. In 1991, Edward Lorenz received the Kyoto Prize. At the award ceremony, his chaos theory was described as the most dramatic change in humanity's view of nature since Isaac Newton. So what is the Feigenbaum constant? It is a constant that can be found in apparent chaos. This is evident with a simple system. We look at the so-called logistic function. This is a function used to model the growth of a population, for example, rabbits. It's a recursive formula where the value you're looking for depends on the previous one. AN stands for the number of living beings in generation N. The number of living beings in generation N is the number of ancestors multiplied by a growth rate. Another value is multiplied to this. This ensures a possible upper limit. Capital K stands for the maximum number that animals can ever reach. Because animal species can't reproduce endlessly, they get eaten, suffer from old age, or there isn't enough habitat for them. If you don't look at the total number of living beings, but instead at the percentage in relation to the maximum, you can simplify the equation even further. That means our AN now represents the percentage of the maximum, not just the number of animals. This also means that the maximum possible number of animals becomes 1. That's just for background, so it's clear why it's relatively intuitive and describes a simple dynamic. What is being done now? You start with a starting value, that is, a percentage of the maximum, and put that into the equation. The result is used again. This is repeated over and over. So how do the results behave? This diagram shows, for different growth rates, which number is approached in the long term. For a fixed growth rate between 1 and 3 after a short settling period, convergence to a fixed number can be observed. That makes sense when applied to populations. In nature, animals have a stable population over many generations. Starting from a growth rate of 3, something peculiar happens. Instead of the number of living beings converging to a single value in the long term, it jumps back and forth between two values. For example, in 1 year, it could be 70% of the total number, the next year 30%, then 70% again. This could be explained by the fact that some populations have cycles and can be more or less numerous depending on the year. With a growth rate of just under 3.5, the number of living beings jumps back and forth between 4 values. If you further increase the growth rate, there are 8 values. Then 16, 32 and 64. What's happening here? Zooming in would reveal this in the diagram. The interesting part comes now. The branching into more and more values happens at increasingly shorter intervals. That's why the right part of the diagram is incredibly chaotic. Still, an order is evident. The next interval is about 4.66 times shorter than the previous one each time. The Feigenbaum constant, named after the American physicist Mitchell Feigenbaum. In a 1978 paper, he demonstrated that the ratios of the distances converge to the Feigenbaum constant. Although Feigenbaum knew it, he could not prove that the constant was universal in such dynamical systems. While at first there was only experimental evidence for his work, for example in medicine with cardiac arrhythmias, it has now also been mathematically proven that this is a universal law of such systems. The Feigenbaum constant is an order that was found in chaos. All of life is pure chaos. But who knows how many constants are still programmed into nature so that more and more regularities can be found? The thought is almost uncanny that perhaps everything that exists follows an order and could, in theory, be calculated.